Now, picture this. A blinding midday sun hanging over the high desert scrub, baking the earth until the ground beneath your boots feels like the top of a wood-burning stove. The ambient air sits at a suffocating 115 degrees Fahrenheit in the shade, but up on the tin roof of a small off-grid cabin, the heat is something else entirely. The metal groans and pops under the intense solar bombardment as sunlight hits that exposed sheet metal at over 1,000 watts per square meter, driving surface temperatures to a scorching 140 degrees Fahrenheit. Inside, the ceiling radiates that heat straight down onto the floor, turning the living space into a slow-cooking convection oven. The air inside becomes thick, dry, and almost impossible to breathe. When one builder decided he was done fighting the desert heat with expensive, power-hungry generators and roaring air conditioning units, he took a step back and looked at the sky. His solution was not to buy a bigger cooling unit. It was to build a second, elevated roof directly over the primary one, leaving a continuous, open 6-inch air gap between the two structures. To the casual observer driving past on the dusty gravel road, it looked absurd. The neighbors openly mocked the effort, laughing at what appeared to be an unnecessary double layer of expensive framing lumber and corrugated metal. They called it an eyesore. They claimed the top structure would act like an airplane wing in the first desert storm, ripping right off the trusses and taking the chimney with it. Here's what everyone missed. That second roof was never built to keep a single drop of rain off the cabin below. Its sole job was to capture sunlight. It was designed to absorb the violent, radiant energy of the desert sky and trap the heat before it could ever touch the real roof envelope beneath it. By elevating a continuous metal parasol 6 inches above the thermal shell, the builder unlocked a hidden principle of fluid dynamics. Sunlight hits the upper shade roof, heating the top sheet of metal instantly. But instead of conducting that heat directly down into the rafters and ceiling joists, the energy hits a wall of moving air. As the air within that 6-inch gap warms up, it becomes lighter than the surrounding atmosphere. It begins to rise, rushing up toward a continuous ridge vent running along the apex of the structure. This sudden upward movement creates a low-pressure zone at the bottom eaves, drawing cooler air in through heavy mesh-lined soffit vents at the base. Without a single electric motor, solar panel, or mechanical fan, the double roof system activates a self-sustaining convective engine. The hotter the sun shines on the top roof, the faster the air sweeps through the hidden channel below it, carrying away hundreds of BTUs of thermal energy before it can ever penetrate the living space. While the outer shade shell sizzles in the brutal desert light, the inner primary roof remains sitting peacefully in continuous shade, dropping the radiant heat flux entering the cabin by an astounding 40 degrees Fahrenheit. Think about that for a second. 40 degrees of radiant surface heat eliminated purely through the natural laws of thermodynamics, gravity, and airflow. The homesteaders who built out the American wilderness over a century ago understood this constant battle against the elements. Long before rural electrification brought high-voltage power lines and noisy compressors to the backwoods, surviving extreme climates required a deep respect for passive structural design. In the Deep South, early settlers constructed dog-trot cabins with wide central breezeways, forcing passing winds through the center of the home to draw out hot, stagnant air. In tropical military outposts and remote field stations, engineers built double-ceiling structures and elevated parasol roofs to protect personnel from relentless sun exposure. Yet as modern construction materials evolved, builder priorities shifted away from basic environmental physics. The rise of cheap energy and synthetic insulation led to a dangerous assumption that any climate control problem could be solved simply by throwing more power at it. Modern home builders began packing heavy insulation between standard ceiling rafters, believing that higher resistance values alone would keep the summer heat at bay. But standard thermal insulation does not block radiant energy from entering a roof deck. It merely slows down the rate of conduction. During an extended high-desert heat wave, a standard single-roof cabin undergoes a process known as thermal saturation. Step by step, hour by hour, the relentless morning sun pours shortwave radiation into the dark shingles or sheet metal. That surface heat transfers down into the roof decking, soaking through the plywood and deep into the thick layers of fiberglass or cellulose insulation. For the first few hours of the morning, the insulation holds the line, absorbing the thermal energy within its fibers. But insulation acts like a sponge. By 4 o'clock in the afternoon, after 8 continuous hours of intense radiation, the insulation becomes fully saturated with heat. Once thermal saturation occurs, the insulation can no longer store any additional energy. It begins re-radiating that trapped heat directly downward into the cabin envelope. Even as the sun dips below the western horizon and the ambient outside air begins to cool, the internal ceiling continues to glow with stored thermal energy late into the night. The interior of the cabin transforms into a lingering heat trap, forcing occupants to endure suffocating indoor temperatures long after the sun has set. Adding thicker layers of traditional insulation without addressing radiant solar gain simply delays the onset of thermal saturation. It does not prevent it. The local builders who laughed at the double roof design were relying entirely on this conventional, energy-intensive mindset. They saw a cabin as a sealed box designed to hold synthetic cooling inside while battling the environment with raw electricity. They believed that building a second, elevated roof was a waste of structural materials, an added wind load liability, and a bizarre deviation from standard regional building codes. They predicted that the 6-inch gap would simply trap dead, stagnant air, turning the cavity into a roasting oven that would bake the primary roof deck even faster than direct sunlight. Let that sink in. The difference between a system that fails catastrophically and one that drops temperatures by 40 degrees comes down to a matter of inches and uninterrupted fluid movement. If an air cavity is sealed shut or restricted by improper framing, the trapped air becomes superheated, transferring immense thermal energy straight into the structure. But when designed with precise geometric proportions incorporating a minimum 6-inch vertical gap, a 4 to 12 roof pitch, and unhindered intake and exhaust pathways, the thermodynamic behavior flips completely. The dead airspace transforms into an active thermal break, converting solar heat into kinetic energy that sweeps the thermal load harmlessly out into the sky. The science was sound, but proving it to a skeptical mountain community would require putting the system through the ultimate trial by fire. The hum of a gasoline generator echoed across the clearing as the circular saw bit into dry Douglas fir framing lumber, spitting trails of sweet-smelling yellow sawdust across the sun-baked dirt. Constructing a true double roof is not a matter of simply tacking extra metal over existing rafters. It requires a complete structural rethink, building 2 independent roof planes that coexist on a single timber foundation without compromising the load-bearing integrity of the cabin walls. The first challenge began at the top plate, where heavy-duty timber trusses had to be anchored deep into the wall frames to handle both the static weight of the double layer and the dynamic uplift forces generated by high-altitude desert winds. Step by step, the primary thermal shell was constructed first. Workers laid down heavy ceiling joists, topped with high-density plywood decking and an impenetrable synthetic weather barrier designed to keep the cabin sealed tight against rain, snow, and air infiltration. This was the true roof of the house, the sealed envelope. But instead of laying corrugated steel directly onto this primary deck, the builder began mounting vertical cedar sleeper joists, elevating the secondary framing 6 full inches above the primary deck. Every single fastener penetrating that primary weather barrier had to be sealed with high-temperature butyl flashing tape to guarantee that moisture would never creep into the lower ceiling envelope. The physical labor under the blazing midday sun was punishing. The sheet metal for the upper shade roof became so intensely hot to the touch that crew members had to wear thick leather work gloves just to hoist the panels into position. A single slipped panel or dropped tool meant scorched skin or damaged flashing. Every cut had to be exact. If the air gap narrowed down to 2 or 3 inches near the eaves, the fluid dynamics would break down, creating a mechanical bottleneck that would restrict airflow and trap superheated air over the primary deck. To maintain a continuous 6-inch cavity across the entire surface of the roof, the framing required custom-notched structural standoffs. These standoffs allowed air to travel completely unobstructed from the lower eaves all the way up to the apex. Along the entire length of the lower intake perimeter, heavy stainless steel mesh featuring an 1/8-inch grid pattern was installed to guard the intake cavity. In the high desert, an unsealed 6-inch dark wooden gap is an open invitation for mud daubers, wasps, squirrels, and birds to build nests that would instantly block the airflow or create a severe fire hazard from dry nesting materials. Beyond pest mitigation, the secondary shade roof presented a major structural engineering hurdle: extreme wind uplift. A secondary roof raised 6 inches above a primary surface creates an ideal airfoil profile. During severe summer thunderstorms or high-velocity desert updrafts, strong winds rushing over the peak can create immense negative pressure above the upper sheet, while high-pressure air collects within the 6-inch gap underneath it. Without proper structural engineering, this pressure differential can peel an elevated roof structure right off a cabin like the lid of a tin can. To counteract these massive uplift vectors, the builder installed heavy-gauge galvanized steel hurricane ties and diagonal shear bracing at every major truss intersection. Every single connection was calculated to withstand wind gusts exceeding 90 miles per hour. The upper shade roof was wrapped in lightweight, reflective galvanized corrugated steel, intentionally chosen for its low thermal emissivity and high resistance to ultraviolet degradation. The result was a dual-layered architectural system, a structural parasol suspended over an isolated thermal sanctuary. Understanding why this double roof system performs so exceptionally well requires peering beneath the surface into the invisible world of fluid mechanics and heat transfer. Thermal energy moves through a building envelope in 3 distinct ways: conduction, convection, and radiation. Traditional home building focuses almost exclusively on conduction, the transfer of heat through solid materials like wood, drywall, and insulation. But during intense summer months, direct electromagnetic radiation from the sun is the dominant force driving heat into a home. When solar radiation strikes the upper galvanized steel roof, the metal absorbs that radiant energy and attempts to transfer it downward. In a standard single-roof home, that heat conducts straight into the roof decking and attic space. But in the double-roof system, as soon as heat radiates off the underside of the upper metal sheet into the 6-inch air cavity, it encounters the principles of fluid dynamics governed by Bernoulli's equation and the thermal stack effect. Air inside the 6-inch gap absorbs heat from the upper metal skin. As molecules warm, they expand, lose density, and rise naturally toward the higher elevation of the roof pitch. The steeper the roof slope, the faster this warm air accelerates upward. As this rising mass of superheated air exhausts out through the continuous ridge vent at the peak, it generates a localized pressure drop within the cavity. This pressure differential continuously pulls cooler, denser ambient air through the stainless steel-lined soffit vents at the bottom eaves. The air velocity inside that narrow air gap can reach speeds of several feet per second purely on buoyant convective force, sweeping away up to 80% of the radiant heat load before it can ever touch the primary roof deck below. However, introducing aggressive passive air movement across a roof structure introduces a critical, life-threatening engineering challenge that many off-grid builders overlook: the risk of carbon monoxide poisoning. In an off-grid cabin utilizing a wood stove, propane heater, or secondary combustion appliance, chimney draft relies entirely on natural pressure balance. A flue pipe functions because warm, lightweight exhaust gas inside the pipe rises, creating a gentle negative draft that pulls toxic carbon monoxide gases out of the firebox and venting them safely above the roofline. When an aggressive passive cooling system like a double roof is operating at peak fluid velocity during hot or transitional weather, the powerful upward draft through the 6-inch roof gap can generate a strong localized vacuum at the roofline. If a wood stove or heating appliance draws its combustion air from inside the cabin without a dedicated external intake, this powerful roof draft can invert the chimney's natural updraft. The low-pressure zone creates a reverse siphon effect, literally pulling toxic, odorless carbon monoxide back down through the flue pipe and spilling it into the enclosed living quarters while the occupants sleep. To eliminate this deadly hazard, the builder implemented a strict, non-negotiable safety specification. First, a dedicated sealed exterior fresh air intake duct was routed directly from outside the cabin walls into the combustion chamber of the heating appliance. This completely isolated the stove's air consumption from the pressure dynamics of the interior room. Second, the heavy-duty stainless steel combustion flue could not simply terminate in the middle of the air gap. It had to pass continuously through both roof planes. Passing a high-temperature chimney pipe through two separate structural roof decks creates a major fire hazard if not executed carefully. The builder installed double-wall, factory-insulated Type HT stainless steel flue pipe, rated to withstand internal chimney fires up to 2,000 degrees Fahrenheit. Where the flue penetrates the primary lower roof deck, a high-temperature silicone boot and non-combustible fire stop thimble were installed, maintaining a strict 2-inch clearance to all wood framing. The chimney then extends vertically through the 6-inch open-air cavity, fully shielded against the rushing, cooling air, before passing through a second weatherproof stainless steel flashing assembly on the upper shade roof. To complete the safety system, battery-backed carbon monoxide detectors were installed at two distinct elevations within the cabin, one at sleeping height near the bed and one near the highest point of the interior ceiling, ensuring continuous air monitoring. By respecting the rigid laws of both thermodynamics and combustion safety, the cabin was rendered both thermally efficient and completely safe for year-round habitation. By late August, the desert atmosphere had turned dry as bone, transforming the entire valley into a shimmering, sun-baked pressure cooker. Weather advisories blanketed the region as an unprecedented heat dome settled over the high basin. Day after day, ambient air temperatures climbed past 112 degrees, peaking at an extraordinary 118 degrees in the shade. Out on the county road, power lines sagged under the immense strain of thousands of regional air conditioning units running at maximum capacity. Then, at 2 o'clock on a Tuesday afternoon, the regional electrical grid collapsed under the overload. Transformers blew, substations tripped, and power vanished across the entire district. In neighboring homesteads and modern off-grid setups relying on heavy battery banks and central cooling systems, panic set in fast. Within 2 hours of the blackout, power-hungry cooling units sat silent. Indoor temperatures inside conventional homes began to skyrocket. Heat soaked through dark asphalt shingles, saturated the ceiling insulation, and began radiating down into living rooms like an iron skillet left on a burner. By late afternoon, families were forced to abandon their indoor spaces, retreating to porches to escape the suffocating air inside their own homes. Meanwhile, at the double-roof cabin, the extreme weather was performing an entirely different kind of miracle. The hotter the sun beat down from the cloudless sky, the more aggressive the passive cooling system became. Sunlight struck the upper corrugated steel roof, sending surface temperatures climbing to a blinding, blister-inducing 158 degrees Fahrenheit. But instead of transferring that unbearable thermal load down into the cabin framing, the intense heat activated the convective air gap with incredible power. Walking along the side of the cabin, you could physically feel a steady stream of hot, dry air rushing out from the continuous ridge vent at the peak, sweeping away thermal energy as fast as the sun could deposit it. Inside the living room, there was no hum of fans, no roaring generators, and no cold air blowing from ductwork. Yet the air remained astonishingly still, dry, and cool. Standing beneath the exposed wooden rafters, the interior felt like a deep cave carved into the side of a canyon, completely isolated from the blinding white furnace raging on the roof above. The numbers don't lie. The true mechanical performance of the double roof structure during the peak of the heat wave was verified by a comprehensive thermal audit using a calibrated, forward-looking infrared camera and precision surface contact probes. The data gathered across the structural envelope revealed the precise impact of continuous passive convective cooling. The infrared camera painted a stark, fascinating visual picture of thermodynamic principles in action. On the outermost layer of the structure, the top galvanized steel shade roof glowed bright white and yellow on the thermal display, reading a staggering 158 degrees Fahrenheit under direct solar radiation. Just 6 inches below that scorching metal sheet, inside the open-air channel, thermal sensors registered the rushing airstream at 112 degrees, matching the ambient outside shade temperature, as fresh air was pulled in from the eaves and exhausted out the peak. The most dramatic data point appeared on the surface of the primary lower roof deck underneath the shade roof. While the outer skin boiled at nearly 160 degrees, the primary weather deck sitting in continuous shadow registered at just 98 degrees Fahrenheit. The 6-inch vented air cavity had successfully eliminated a mind-boggling 60 degrees of direct surface heat, preventing 40 degrees of radiant thermal flux from ever penetrating the ceiling envelope. To understand why this reduction is so critical, we must look at the Stefan-Boltzmann law, which dictates that the radiant energy emitted by a surface is proportional to the fourth power of its absolute temperature. By dropping the temperature of the ceiling surface from 142 degrees to 92 degrees, the radiant heat flux into the living space was cut by more than half. At the interior ceiling plane, surface temperatures stabilized at a comfortable 76 degrees. By preventing thermal saturation before it could start, the cabin maintained a stable, livable sanctuary without consuming a single watt of electrical power. But the scorching heat of August was only one half of the thermodynamic trial. As the seasons turned with violent suddenness, the blazing high desert basin transitioned into a brutal, high-altitude alpine winter. By late December, the blistering wind was replaced by a sub-zero draft sweeping down from the mountain peaks. A historic, record-breaking winter storm hit the valley, dropping 4 feet of heavy, wet snow in 36 hours, accompanied by winds exceeding 60 miles per hour. This waterlogged blanket of snow exerted immense physical pressure on the roofs, weighing nearly 20 pounds per square foot. Inside their homes, the neighbors built roaring fires in their wood stoves, desperate to hold back the freezing temperatures. But as their cabins warmed, a destructive physical crisis began to unfold on their single-skin roofs, the phenomenon of ice damming. Because their roofs had no thermal break, interior heat conducted straight through the ceiling into the roof deck, melting the bottom layer of snow. This meltwater ran down the sloping roof, hidden beneath the snowpack, until it reached the cold overhang of the eaves. Exposed to the sub-zero air, the water froze instantly, forming a solid barrier of ice along the edge of the roof. Subsequent meltwater backed up behind this ice dam, creating standing pools of liquid water that seeped through the seams, dripping into their ceilings, soaking their insulation, and causing structural joists to warp and buckle. But at the double-roof cabin, the open 6-inch air gap was performing its winter role with identical efficiency. While Frank kept his wood stove burning hot inside, the thick insulation on his base deck slowed the conduction of heat. Any residual thermal energy that did escape was immediately swept away by the freezing sub-zero air circulating through the open eave vents and out the peak. Because the air cavity remained cold, the outer corrugated metal roof stayed at exactly the outdoor freezing temperature. The snowpack resting on the outer roof did not melt from the inside, completely eliminating ice dams. The snow remained frozen and stable across the entire pitch, draining cleanly when the sun emerged without ever backing up or penetrating the home. Inside, the cabin was a dry, safe, and warm sanctuary. The Class A Type HT triple-wall chimney pipe drafted perfectly, holding its inner heat to maintain an upward draw while keeping its outer surface cool enough to prevent any fire hazard at the wood penetrations. And with the sealed outside combustion air intake feeding the firebox directly, the wood stove operated with maximum efficiency, completely unaffected by the extreme wind shear howling across the double roof peak. True off-grid independence is not about building complex, fragile mechanical systems to fight against the forces of nature. It is about understanding the fundamental laws of physics and letting the environment do the heavy lifting for you. For decades, modern construction has relied on brute force spending vast amounts of energy to pump heat out of poorly designed structures, while ignoring the primary solar dynamics acting on the building shell. The double roof cabin stands as a quiet, powerful reminder that simple geometric principles and respect for natural fluid movement can outperform the most expensive high-tech cooling systems on Earth. Alongside this, building a self-sustaining home requires a deep commitment to both efficiency and uncompromising structural safety. Anyone attempting to implement passive thermal breaks or elevated roof systems must carefully consult local structural engineering standards, account for extreme regional wind load conditions, and enforce strict safety protocols for all heating flues and combustion appliances. With proper design, dedicated carbon monoxide detection, and a clear understanding of heat transfer, a home can become more than just a shelter. It becomes a permanent, resilient haven capable of standing calm and comfortable against whatever climate challenges the sky may bring.